Hello everyone, I'm J Wildberger. This is our second video in this series on understanding infinitesimals in a really solid way. And the key is going to be to looking at these dual complex numbers, which we'll talk more about today. And I want to bring this towards the theory of differentiation, and especially the Leibniz differentiation rule. So we're going to talk about the derivative today, but in a much broader setting than you're used to. So a lot of this overlaps or extends some of the things we've been talking about in the Algebraic Calculus 1 course, and we'll be talking about more of in the Algebraic Calculus 2 course. So if you don't know about those things, please make contact with that. A great opportunity to really expand your understanding of calculus in a major way. Okay, so we're working very generally over a field, F, and we're looking at this algebra of dihedrons, 2x2 matrices with entries in the field. And inside that algebra, there's this two-dimensional subalgebra, which we're calling C sub D. These are the dual complex numbers. They're things of the form A0BA. We can recognize that as being A times the identity matrix plus B times epsilon, where epsilon is this very simple matrix here, 0, 0, 1, 0, just a single non-zero entry in that bottom left corner. Now, this algebra, more or less introduced first by William Clifford, 1873, a major pioneer in sort of the development of geometry in an algebraic fashion into higher dimensions, especially along with Grossman. Okay, and we're purporting that this epsilon, which is actually just this explicit 2x2 matrix, is really acting as an algebraic infinitesimal. And that's going to be the key point in moving towards a precise theory of infinitesimals, is to make contact with these dual complex numbers, in particular this one right here. So we want to move towards deriving Leibniz's famous differentiation rules, but in this much wider context of polynumbers or polynomials over F, over a general field. So polynumbers are my preferred way of thinking about polynomials. These are sort of fundamental kinds of functions when you're dealing with this very kind of general setup, and I'll explain a little bit more about that shortly. But here are the rules that we're aiming towards. So these are very familiar to any student of calculus. D is the differential operator. Okay, the derivative of a sum p plus q is the sum of the derivatives. The derivative is linear. If you multiply by a scalar, it comes out. Then there's this important product rule that the derivative of the product p times q is p times the derivative of q plus q times the derivative of p. And the derivative of a power is given by this formula. D of p to the n is n times p to the n minus 1 times the derivative of p. And then the chain rule, the derivative of the composition p circle q, is the derivative of p evaluated at q times the derivative of q. Okay, so we want to first get a sense of what these objects are that are the ingredients for this, and then we want to understand how we extend the usual notion of derivative to this more general situation. And we're going to see that these dual complex numbers play a crucial role to do that. All right, so here's the usual story, okay, presented to calculus students all around the world. The differential calculus is about functions, typically over the real numbers. For example, f is a function on an interval I. So we're supposing that we know this crucial word function, which is actually highly problematic. But we picture something like this. Here's the usual xy plane. Here's some interval. This function f is defined on it. There's the graph of it. There's a point C. And maybe we're interested in the tangent to the curve at the point C. Its slope is the derivative of the function at C. So that's the geometrical meaning. Okay, the actual official definition is like this, that the derivative of f at the point C, okay, is a certain limit of a certain quotient. You take f of c plus h minus f of c divided by h. So h is some typically small quantity. In this case, it will be negative, but it can be either positive or negative. You take the difference between the function's values here and here, so that difference in y values. You divide by the difference in x values, which is h. That gives you then the slope of this secant line, and then you let h go to 0, and that means this point is moving towards there. So this is these days expressed in terms of a limiting process. Okay, introduced in some fashion by Cauchy and then in sort of a different fashion by Weierstrass. But the current framework is that of Weierstrass, which is all based on this yoga of epsilon delta calculations, which are invariably illustrated in very simple situations, but actually if you look at the actual definition, it involves an infinite amount of work. So there's all kinds of problems with this scenario, starting of course with the fantasy aspect of the underlying number system, real numbers. Okay, then the idea of a function. What exactly is a function? Okay, the modern notion of a function is quite different from Euler's notion of a function. It's more of a pointillist kind of thing where you just ascribe real number values to real numbers. So the modern mathematician thinks of a function as some kind of list of real numbers x and corresponding other real numbers f of x. It's not really even a list because it's too big to even fit inside a list, but it's a completely fantastical unobtainable kind of object, but it supports our intuition, supposedly. Okay, and then this notion of limit definitely requires infinite numbers of calculations, even though the toy examples that are presented to undergraduates are so simple that you can get away with hiding this, so that the undergraduate thinks, oh, we're just playing a little bit of algebra, cooking up a formula for the delta in terms of the epsilon, etc. But it's a really a misrepresentation of the true complexity of this story. Okay, so there's a lot of things that are wrong with this. This certainly has not attained some kind of height of rigor as people try to imagine. Okay, no way, not even close. Okay, we really seriously need to rethink pretty well everything that's on this page. And that's what the algebraic calculus does. Okay, it provides real alternatives to this story. And a great place to start is to think more generally and think more algebraically. So to explain the framework, I have to tell you about polynumbers. Okay, and that's a very concrete way of addressing what a polynomial is, avoiding the crucial difficulty of saying what a variable is. Okay, saying what a variable is so complicated. What's a variable? X is a variable. Y is a variable. Dependent variables, independent variables, setting variables equals to constants. There's all kinds of problems as to what the meaning of the word variable is in mathematics. We want to avoid that, okay? And we can do that by adopting almost a data structure kind of point of view towards things. So the fundamental object, a polynumber over a field F. It's an object that looks like this. It's a list, a vertical list of numbers, A0, A1, A2, all the way up to A sub k. And all of these numbers are elements in whatever field we're working over. And we'll agree to put it into some kind of framework like this. So there's kind of a top, but there's not a bottom. Okay, so it has a kind of an open-ended aspect as you go down. And that's to reflect the fact that if you added a 0 as the next entry, that would, by agreement, not change the polynumber. Okay, so we agreed to allow extra zeros, or to allow ourselves to rub off zeros at the bottom. Okay, and the polynumber alpha is kind of a key polynumber. It's the polynumber 0, 1. Okay, it's sort of like the second simplest polynumber. The simplest polynumber is where you just have a 1 at the top. That's like the number 1 in some sense. This is sort of the next step down. It's alpha. So alpha is, in this case, just a particular polynumber. Okay, so then we have arithmetic with these things. So the addition and scalar multiplication are element-wise. So is subtraction. Subtraction with a T. Okay, so illustrating addition. So here is a polynumber. 3, 1 bar, 2. I remind you that I like to use bar sometimes for a negative sign. Instead of saying -1 or -1, we can put 1 bar. It's sometimes a little bit more efficient to use that form of negation. So suppose we have 5 times the polynumber 3, 1 bar, 2, and we want to add that to the polynumber 4, 2. These are different sizes, okay? That doesn't bother us. So we add component-wise. 5 times 3 plus 4 is 19. 5 times -1 or 1 bar is -5 or 5 bar. If we add 2, we get 3 bar. And then the next row is 5 times 2, and there's nothing here, so we just think of that as being like 0. So we have 5 times 2 is 10. So there's the sum and also scalar multiple exhibited that way. The really interesting part is the multiplication, which is trickier. That's the Cauchy product. Okay, so illustrated here with this example. So here we have two more polynumbers, 1, 2 bar 5, and 4, 1. How do we multiply them? We start from the top. The top, the 0th element up here, is the product of the 0th elements here, 1 times 4. The 1 element is the product of the 0 element here and the 1 element here. That's 1 times 1. And plus the product of the 1 element here and the 0 element here. So that's plus -8 for a total of -7 or 7 bar. The next entry, which is sort of like the level 2, okay, is obtained by taking the 0 level guy times the 2 level guy. There's only a 0 here, so that's 0. Plus the 1 level guy here and the 1 level guy here, so that's -2. Plus the 2 level guy times the 0 level. That's 20. So 20 minus 2 is 18. But we can keep on going. So the 3 level fellow will be the 0 level times the 3 level. That's 0. The 1 level times the 2 level. The 2 level times the 1 level. That's 5. And the 3 level times the 0 level. So you see we're taking products of terms so that the sum of the levels is the level that we're aiming for over here. So the result is 4, 7 bar, 18, 5. And that exactly corresponds to how you would work this out if you wrote this out in powers of alpha. So this thing here can be written out as 1 minus 2 alpha, that's like alpha, and this thing here is like alpha squared. If alpha is 0, 1, then alpha squared is 0, 0, 1. And so this is actually 1 minus 2 alpha plus 5 alpha squared, and this one is 4 plus alpha. And then if you multiply those out with the usual polynomial rules, okay, you get exactly the same thing. So the Cauchy product is just a data structural way of capturing the way we usually multiply polynomials. But crucially, this alpha that's floating around here is not some kind of variable. Okay, it's not a variable. It's actually this particular
crucially,
a polynumber is not a function. It's just an expression. It's actually just a column of numbers, with the top one being like a regular number and these numbers below it sort of higher numbers, or actually perhaps lower numbers. But nevertheless, we can connect polynumbers with functions through evaluation. So let's look at it through an example. Suppose we have this polynumber p, which is 4 plus 2 alpha plus alpha cubed. So I'm writing it in what we might call polynomial form as a linear combination of increasing powers of alpha. Okay, but we could write this also as a vertical list. It would be the vertical list 4, 2, 0, because there's no quadratic term, 1. Okay, so this particular polynumber can be evaluated at an element c, say, in our field. How do you do that? Well, p of c is what you get when you replace the alphas here with c. So you get 4 plus 2c plus c cubed. So this thing can be interpreted as a function. You could input a number c, a number meaning an element in your field, and you're getting another element in the field. But it's actually more flexible than that, okay? It could also be evaluated at other things as well, including at matrices. So let's go back to our dihedrons. And inside our dihedrons, we have these dual complex numbers of the form a plus b epsilon. Okay, so that was a particular 2 by 2 matrix. So we can also evaluate p at this dual complex number. How? Well, exactly the same thing. You just replace the alpha in the expression here with a plus b epsilon. So 4 times 1, we might be a little bit specific about that. So the 1 here is the identity matrix because we're working in the algebra of matrices. We could be even more specific about that by being a little bit more pedantic about this. Instead of writing 4 times alpha to the 0. Okay, if we did that, then that little ambiguity would disappear. So we have 4 times the identity matrix plus 2 times a plus b epsilon plus a plus b epsilon cubed. So this is then a matrix calculation. It's happening in the world of 2 by 2 matrices, not in the world of numbers up in the field. Okay, but that's fine because it's only algebra and we can do algebra in this algebra of 2 by 2 matrices. So the constant term, in other words, the stuff that doesn't involve epsilon, is going to be 4 plus 2a plus an a cubed from here. So that's going to be like the constant term, or maybe sometimes called the scalar part of the dual number. Okay, and then there's another stuff involving epsilon. So there's going to be an epsilon from here, a 2b epsilon coming from here. And over here, when we expand this out with the binomial theorem, okay, binomial coefficients are 1, 3, 3, 1. Okay, so the next term will be 3 alpha squared times b epsilon. So we get a 3 alpha squared b also times epsilon. But there will be then some other terms too. There will be higher powers of epsilon. The other powers or other ingredients involved in the binomial expansion of this. But they are all going to be 0 because epsilon squared happily is 0. So if epsilon squared is 0, then epsilon cubed is also 0, and all higher powers are 0. Right? So immediately the computation stops there, and that's the answer. What does it actually look like as a matrix? Well, this is that multiple of the identity matrix. So there you see that on the diagonal. And this is the multiple of epsilon. So there's going to be a 2b plus 3a squared b down here in this corner and a 0 up there. That's the result of evaluating this polynumber on this dual complex number. We get another dual complex number. It's a combination of 1 and epsilon. So what about the derivative? The derivative was actually first introduced not by Leibniz or Newton or the contemporaries involved in the birth of the calculus. It was actually introduced by Johann Faulhaber, a German mathematician who lived from 1580 to 1635. And he introduced the derivative as a purely algebraic operation on polynomials. This was for some investigations he was making on sums of powers of natural numbers. And you can read about that in my Algebraic Calculus 1 series. Okay, so here's the basic definition of the Faulhaber derivative. That if you look at the polynumber alpha to the n is a natural number, 0, 1, 2, etc., then the derivative of that is n times alpha to the n minus 1. With the interpretation that when n happens to be 0, okay, this 0 coming down here means that the whole thing is 0. This is then extended linearly to polynumbers more generally. So for example, the derivative of 4 plus 2 alpha plus alpha cubed is the derivative of the constant 4 plus 2 times the derivative of alpha plus the derivative of alpha cubed. The derivative of 4 is 0 because that's like the case alpha to the 0. The derivative of alpha is just 1, so we get 2 there, and the derivative of alpha cubed is 3 alpha squared. So the derivative of this polynumber is 2 plus 3 alpha squared. A purely algebraic operation that has, at least initially, nothing to do with slopes of tangent lines or limits of quotients. Now, if we return to p equals 4 plus 2 alpha plus alpha cubed, then I remind you that we've earlier calculated that p of a plus b epsilon is this first part, not involving epsilon, which is just p of a. And then there's a multiple of b epsilon, and that multiple we can rearrange and get 2 plus 3a squared. At which point we recognize that this multiple of b epsilon is exactly the derivative of p evaluated at a. So it looks now that we can connect the Faulhaber derivative with the more usual interpretation of the derivative using this infinitesimal algebra. So if we replace this particular p with a general polynumber q, it looks like what we're getting is that if we're interested in the derivative, we could solve this kind of equation for the derivative. If we bring this to the other side and then divide by b epsilon, then we would isolate this term. Okay? So the derivative of q at a, you might expect would be q of a plus b epsilon, that's what's over here on the left-hand side, minus q of a, that's that part there, divided by b epsilon. So formally, this is sort of a rewrite of this, where I'm using q more generally rather than p. Now, when we do this, we do see that there is a natural connection with the usual quotient involved in the limiting definition of the derivative, or even the geometrical definition of a derivative as a slope of a tangent. But is this kind of equation really justified? Is its meaning clear? Well, no, it isn't. Because in the world of infinitesimals, this dual complex number world, this thing here, which is on the bottom, this b times epsilon, is really representing this matrix. So remember, epsilon was the matrix 0, 0, 1, 0, so b times epsilon is 0, 0, b, 0. That matrix in the 2 by 2 world is not invertible. You're not allowed to divide by it. Okay, this is the kind of objection that 18th century people like Bishop Berkeley were making. You're dividing by this thing which is kind of between 0 and not. Is that really allowed? So here in this very concrete algebraic situation, we can see that there's a problem with this because we're attempting to divide by this quantity which is not officially invertible. But nevertheless, this sort of rudimentary calculation does connect the Faulhaber, purely formal algebraic derivative, with our more usual understanding of a derivative as a limit of a quotient. So here's an important calculation that directly connects with Faulhaber's original definition. Let's look at the polynumber p, which is just the pure power alpha to the n. N is a natural number. And then let's look at p of a plus b epsilon, this general dual complex number. Well, it's just what you get when you substitute this in for alpha. So we get a plus b epsilon to the n. And now we can use the binomial theorem. This is essentially the binomial theorem here. So we get a power of a, we get a to the n, and then n choose 1, that's like the constant, times a to the n minus 1 times this term here, b epsilon. And then the next one in the series will be n choose 2 times this thing to the n minus 2 power and this thing to the 2 power. And we keep going. The binomial coefficients go on as before, and the powers of a's decrease, the power of b epsilon increases. Until the last one, we just have only powers of b epsilon. We have b epsilon to the n. Now, happily, almost all of these terms are 0 because of the crucial property that epsilon squared is 0. So this term here will be 0 because there's an epsilon squared involved. And the next term will have an epsilon cubed, which will also be 0, all the way up to this one here, which has an epsilon to the n, that'll also be 0. So the only thing that remains are the first two terms, a to the n plus n, because that's n choose 1, times a to the n minus 1 times b epsilon. And so now we see this is consistent with what we were sort of seeing before, that we are getting p of a plus some multiple of b epsilon, and that multiple is indeed the derivative of p evaluated at a. That's exactly Faulhaber's formula obtained in this sort of semi-miraculous fashion with playing around with the algebra of these dual complex numbers. Now remember, one of our aims here is to try to extend calculus to a wider situation, including the possibility of more general fields, especially finite fields, which is very exciting because then all of our intuition about continuity and rates of change and so on are suddenly in question. But nevertheless, algebraically, there is at least the possibility that this is going to support a very rich kind of calculus once we get our heads around it. Now, at this stage, however, a hurdle appears that we have to be aware of. And it's a hurdle that's a little bit unfamiliar to most undergraduates because they usually don't work in the context of calculus with finite fields. The hurdle is that there's a usual correspondence between what we're calling polynumbers and what are usually called polynomial functions. So if we have some polynumber p, then we've seen that we can evaluate that p at, say, a number. And then that evaluation yields for us what we might call a function. And it's a polynomial function because it started with a polynumber. Now, in some approaches to mathematics, the function is considered sort of the primary thing. That's what a polynomial is. And so in some courses, you see that the definition of a polynomial is that it's a function of a particular kind given by a certain form. Our approach is to try to separate the functional aspect from the data structure point of view. Okay? And when we get to the idea of a derivative over a finite field, this separation becomes important. We have to decide whether we're looking at things from this point of view or from this point of view, because they are not exactly the same. So that's something that requires some explanation. Okay, so we are going to have to venture a little bit into the world of polynumbers over especially finite fields to see what the problem is here and to understand how we should think about the derivative as really belonging to the world of polynumbers. In other words, you sort of have to extend the kind of calculations that we've been doing today, which is more or less at the level of functions, and move up a level to render them as calculations in the world of polynumbers themselves. Very interesting. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.